All right, welcome back, friends. This is William M. Briggs. This is Uncertainty and Probability Theory, the Logic of Science. This is episode or class 32, The Evils and Errors or Errors and Evils and Excesses of Epidemiology 2. Let's do a real brief review of what we did last week, a real brief review, and then I want to get to some of the questions and very excellent comments. I'm starting to get some critical commentary on some of these lectures, and my heart soars like a hawk. I love them. Keep them up. They keep me sharp. They keep you sharp. They keep everybody going. So let's look at some of this again. So we're talking about a field that tries to turn correlations into causations. And in a way which we haven't learned how to deal with yet either, something called hypothesis tests and all this kind of thing, or the equivalent confidence intervals around parameters and models and the like. We're not going to deal with any of that. We're just dealing with it on a kind of a surface level, looking at the basic mistakes that the field itself makes. And so we're going to review what we did, and I'm going to cover how they should be doing it, how it can be done, and isn't because of the difficulties we'll come to. And then I don't even think we'll get to this time to the most egregious error of epidemiology, and that's the so-called ecological fallacy, which I call the epidemiologist fallacy, which is the same as the ecological fallacy, but married with a p-value, when a scientist goes around waving his wee p-value at you and asking you to be impressed. Well, so we're looking at something here. We're taking a particular paper. This is a paper we looked at. This is a very typical paper. This is not known to some people, but it is not at all obscure. I left in the comments last week, and I even said in the lecture, some very major papers put out by Jarrett and others about pollution and heart disease and so forth are along these same exact lines. I'm using this paper, Bonvinci, I'm not quite sure how to pronounce it, because it was used in arguments in government, not our government, but other governments, as being an important paper and so forth. So I'm just not plucking this from the sea of bad papers. There's always bad papers everybody acknowledges, but this one was touted as a reasonable one. And we're going to see that it isn't reasonable. And it makes the same kind of mistakes that lots of epidemiological papers make, but it makes them very plainly and easy for us to see. So I picked it for that reason. So let's remember, we have, we start with some thing, and I say that it looked or sounded suspiciously bad or something like this. And we're going to go and see if we could find measurements that confirm the badness of this suspicious sounding thing. And one of the commenters said, well, you know, we know from cell cytology and so forth that pesticides are bad. And that's a very important point. It's a good point. You know, we could take pesticides and we could drop it on some cells and look at them under the microscope, look at cell damage, we can look at genetical damage and all kinds of things and things like this. But it does not follow from that basic level. It's very good science and it should be done. It's necessary. And it's absolutely positively necessary to prove cause of the substance causing whatever malady it is, whatever disease that we have. And I guess in this case we're doing ALS. But any number of diseases are used in this. Heart disease, Parkinson's is a big one. Any kind of neurodegenerative disease falls under anything at all that you can put in here. Lower IQ scores, all kind of things fall under this. Anyway, so the cytology is one important thing, and we need to absolutely do it. But it doesn't follow that you're going to dose a cell with some incredibly large value of a substance, a bad substance, and some bad things happen to the cell. That's what's going to happen to people in real life. It's a different thing. The body, the way the body handles things, the entire body's in line. And we need to get rid of this mechanistic idea. It's a very grand metaphor, as we talked about in other articles on my wmbriggs.substack.com or wmbriggs.com about how the mechanistic looking at things, if everything was a machine, it has a lot of uses and it provided a lot of good, but it's not the whole story. Bodies are bodies as a whole, as a substance as a whole. And so when some foreign substance comes against the body, it's not that it's going to do the exact same kind of a damage as if you were going to drop that stuff in a single isolated cell. It doesn't work that way. The body comes together in a way to ward off all kind of bad things. So it doesn't follow that because it's bad in cytology that it's necessarily bad for the body as a whole, but it might be. So we need to do all those studies, absolutely. I don't say we don't do them, but we need to do lots more as well. Okay, so we have some disease, we have some background information, whatever it might be related to the area and the people, the population, the kinds of things that we're looking at. And then we have this idea of exposure and dose, a sufficient dose to cause the malady in question. Or possibly cause the malady in question. I don't know what a sufficient dose is. It all depends on the particular substance, depends on the disease, it depends on the person, depends on all kinds of things. But it's not just dose, yes or no. Some people are asking me, well, isn't exposure just yes or no, a dose? That means to say if you're doing pesticides and you have a pesticide can, you're getting it, you're inhaling at least some, maybe. Possibly, and you're touching it, it's getting maybe absorbed through the skin or something like this. All that could be true. Absolutely could be true. So exposure is not a known quantity. It's not a fixed definition, and neither is dose. But we're separating them here. We're not separating them. They are absolutely different things because exposure, particularly in this paper we're looking at here, this was done by questionnaire. We're asking people, do you recall ever coming into in the vicinity of or contact with any kind of pesticides? That doesn't mean that you had any dose at all, not even yes or no. Just because you carry a can of pesticide or from the store to the barn or something like this, it doesn't mean you had any dose whatsoever. That would still be counted as exposure in something like this. So we absolutely need to keep separate the ideas of exposure and dose, and they are going to change depending on the paper. Some papers do look at dose, and they look at levels of dose and things like this. That's not the case with this paper, and it's not the case with a lot of papers. So I'm not saying all papers are like this, but a great many are. Okay, now we looked at this, and we know that exposure is not dose. You need to be exposed before you can be dosed. And we looked at, this is the kind of quantities that epidemiologists calculate. They said, given the people that had the disease and whatever background information we had, we look at all those people. There's 41 people in this particular sample who had the disease or the probable disease. I think some people forgot that. These were all ALS patients in a particular area, a region that we looked at, a region of 150,000, I think it was, something like this. But that number itself was kind of uncertain, so there's an uncertainty there. And they don't, okay, this is another great question. We'll come to this question too. But there were, in this vague population, there were 41 people with ALS or probable ALS. So we have an uncertainty there that's not taken care of in any of the downstream analyses. It just lingers there. Not the size of the population, not the size of the number of the people with disease. All of that stuff is just kind of left floating. And what they'll do is, and then we had 82 people who did not have ALS but were in the hospital or could be surveyed for other reasons. And they were exposed. 11 of them that were exposed out of the 82 of other patients. And so they can calculate, these probabilities are exact now. They're exact probabilities for these particular 41 people. This is the exact probability of the person admitting on a questionnaire they were exposed. That doesn't mean they were exposed or got a dose. This is the exposure in this case means answering yes on a questionnaire. Okay? That has to absolutely be keeping in mind. So they answered yes on a questionnaire. We take those 41 people, we grab one of them out of the room, and the probability that any one of them would have answered yes on that, of those 41 people, is about 32, 0.32, and 0.414 for the people who weren't exposed. Now it should be absolutely positively clear that the probability of exposure given you have the disease or don't have the disease, is not the probability that you have the disease. These are not the same thing. And so one commenter said, well, we can calculate things like odds ratios, and they do things like this. They do this. This is the odds of having exposure in the diseased group and the odds of having the exposure in the non-diseased group, and we take the ratio of those. This applies to just these 123 people here, and not to others. In order to apply it to other people, we have to do more kinds of modeling we haven't yet come to. We haven't learned how to do any of that yet. And we can calculate an odds ratio of 2.9. And they'll say, one person made a very good comment, you know, they do take into account, we have these disparate populations here. They're not the same thing. These were people in the hospital sick for other things, and these are people in the hospital sick with ALS. But they did something called a case control study. Now, we haven't even talked about any of that kind of stuff. I was waving my hands around all that. But the idea is it's an uncertainty because what they'll do is they do these things called table ones. They'll compare the number of males and females in these two groups. And they'll do a hypothesis test. They'll say they were not different. They were different, but they were not significantly different. And then they'll look at the age ranges, and they say they weren't too different. And they'll look at a bunch of other things that they say might be causally related to the disease, and they'll say they weren't that different. And they'll conclude from that that they weren't different. We saw in our randomization videos that that doesn't necessarily mean anything, and that's not proof that they were the same or they were different. And it certainly doesn't come into this kind of stuff. Necessarily. They might have put some of this stuff in a model and so forth and controlled for some of it. Depends on the model. We're not going to get that complicated today. They might have done that, but most often the case, they don't. They have lots and lots of variables that they look at, biological measures, characteristics, and the like, and they'll put 2 or 3 or a handful into a model and ignore the rest, and they'll say they were the same because we didn't get a wee p-value out of it or something. That's not the same. That's not the same as controlling for all forms of uncertainty. But in any case, it's still the wrong number. This odds ratio, this probability, these probabilities are not the right thing. We want the probability you get the disease given whatever background information we have, given you were first exposed, and then got whatever the sufficient dose is. We could do this also by dose levels, right? We could do whatever the dose levels may be. We can graduate them, and we could do this per dose level. But for this particular notation I'm writing here today, just for learning this stuff, we're not going to do that. We're just going to say it's a sufficient dose, whatever it is. Okay, but we can get that. We can get that probability. We can get that calculation. If I can get the cap off this thing. We can get that we can get this, well, we're going to start with this calculation, the probability that they have the disease given they were exposed. Okay, so that's easy. We just use all the stuff we learned. It's the probability they were exposed given they have the disease times the probability of whatever background we have and knowledge we have. And that shows up again in the denominator. Then the probability that they were exposed given they didn't have the disease. And the probability somebody by the background knowledge doesn't have the disease. In this particular study, we can plug all the numbers that we sort of estimated in. If you remember the probability, just on the background information, it's an estimate. We don't know, but we're just going to take this as a guess. The 150,000 and the number of patients that contract over the 11-year period, all that kind of stuff. And we just multiply it out, and we see this probability as 0.0063. 0.0063. That's the probability somebody has a disease given they were exposed. But if we stop there, we'd still be exaggerating things because exposed is not dose. Exposed is not dose. Exposed is definitely not dose. And this particular thing where all we're doing was asking people questionnaires that are sitting in a chair or a hospital bed or something like this. It's not the same. Now, we could also calculate the probability of the disease given they weren't exposed. And that turns out to be 0.0021. We could do an odds ratio of those too, if we like. It's about 3. And it's similar to this one. So we say, oh, they're the same. What's the complaint? Well, the complaint is, the obvious complaint is, here, take a look at this. This is the probability of being exposed given they have the disease, 0.32. Here's the probability of having the disease given they were exposed. It's 3 orders of magnitude smaller. It's 3 orders of magnitude smaller. So if we went with something like this, it's a gross exaggeration. It's a gross exaggeration of the evidence of this thing. And it is some evidence. Exposure comes before dose, and presumably some of the people were dosed. So this is some evidence that this is larger This 0.63 is larger than this 0.0021. It's evidence in favor of this particular pesticide or this group of pesticides causing ALS. It's a correlation. It's a correlation. That's all we have so far is a correlation. But it's not a big effect. But look at what we've learned from this, though. This is the fascinating part right here. Just exposed. And this is 3 times bigger than this. Well, that's what this odds ratio. It's not the risk ratio is just taking one probability divided by another. The odds, you take the odds. They're similar calculations. So this is 3 times as big as this. But this is obviously greater than 0, which means we have proved at least one thing. We have proved at least one thing, that people who are not exposed still have a chance of getting the disease. So there's other causes of the disease that are not related to our pesticides, and they're important to at least this level. And so there is a gap of 0.0004 probability here. That's the gap that's attributable, if at all, to the exposure. But that exposure is merely a correlation with the disease, and it may be just because of other things that people in their lives and their work and all that kind of stuff that were related to the exposure itself that are causing the disease, if so. So we've moved a little bit up. It's always kind of a misnomer. You could put it in this multiplicative way, and this 3 times greater, and that's true. It's a true statement, but it's misleading. If it could be used for propaganda purposes, it's much better to look at these raw numbers. Here's the probability of having the disease given exposure, 0.0006, kind of small. Now what we have to do is the even harder work. We want to, I have to erase some of this. We want to calculate this creature over here, the probability of being, having the disease, having the dose, okay? So let me remove some of this, and I just needed a little bit of space up here, and I'll rewrite it up here. And again, all we do, we just apply our same probability rules. There's no mystery to any of these things. We want the probability of y given. They have the sufficient dose, whatever the sufficient dose is, and the probability, and they were exposed, and they were. I never have my notes in front of me. Okay, yes. Okay, so let me just write this up. This is the probability. Y. This is the thing from here. I'll show you in a second. Times the probability of probability of the dose given y ex divided by probability. Just repeat this. dy ex times the probability of not the disease given ex times the probability of the dose given not that they don't have the disease. And there we go. I'm giving you a second to look at that. We just apply the same probability rules that we've known before, where this creature here, I should use a different color. Where'd my red pen here go? Or orange or whatever color this is. This is this. So we first calculate all this and then plug it into here, and then we can get everything else we need from here. Here comes the problem. Here comes the problem. Well, there's several things to look at here. There's several things to notice about this. If it's the case, capital if here, if the probability of getting a dose in the sick people happens to equal the probability of the dose in the non-sick people, then obviously the probability of having the disease given you were dosed equals the probability of having the disease given you were just merely exposed. So in order for this to be causative, we really want to have this being greater than this. We want to have the probability, given that they were sick, we want this probability to be higher than this. Now, here's the problem. We don't know what these numbers are. For this study, we don't know what these numbers are. And very, very frequently, we don't know what these numbers are because it's a lot of hard work to go out and actually measure people, measure real things, to measure exactly their dose. All right? Next time, tomorrow, the next lesson, we're not going to have time to get to it here. What they do is they say, they know this. I mean, these people are not stupid. Epidemiologists are not stupid people. We're not saying that. They know they lack this, and so what they do is put a model of D in place, a model of D in place, and they estimate whether or not somebody has got D. And then they don't, and they forget it's a model. That's the ecological fallacy. The ecological fallacy is mistaking the probability of exposure and the probability of the disease. They're not the same thing. Here, we don't even know if the person's got diseased, and so they'll substitute a model in this. And there's even greater uncertainty in this model, and it's forgotten in the mad rush to do these things like odd ratios and so forth. So what we really want is we want the probability of the dose to be high. In other words, more people in the sick group got the sufficient dose than this. So I just made up some numbers. I have no idea how plausible these are in this particular study, but we might guess. I just said that this is 0.1. There's a 10% chance of a sick person, the person with ALS, first being exposed. Whatever background knowledge, I'm going to skip saying the background knowledge. It's always there, and it would differ from the study to study because of the background knowledge. But I want the probability that the person is dosed, given they were sick and first exposed. I just made that up and said 10%. I don't know how plausible that is for this particular data. It's just something that looked right, but completely wrong. I don't know. All right, and then I guess 8% getting a dose given they don't have disease but were exposed. In other words, they were exposed, which means they could get dosed, and they were just not dosed as often as the people with the disease. Are these good numbers? Again, I don't know. That's the problem. I don't know. Nobody knows. And we can't calculate the thing we really want to know, which is this, which is the thing that we need to make decisions based on. So let's hurry through that. And if we do all that, and I think, gee, I hope that I worry that the colors can't be seen so easily. So let's just plug these numbers in, plug all the numbers that we have in, and then we come to, I guess we don't need this anymore. Let me get rid of that. Oh, I can't wait to get back to my blackboard, more room. Okay, so just plugging all those numbers in, we get the probability of having the disease, given they had a sufficient dose, whatever that is 0.08, 0008, and we get the probability of, where am I at here? Oh, yes, that's exactly right. And the probability they have the disease, let's remember I erased it, EX, was 0.00063. This is interesting. Here's the probability of having the disease given they were exposed. And here's the probability of having the disease given they were dosed. It's higher, as we would expect, if these numbers, it's all conditional on these numbers, right? Remember, for we did a million times, probability is dependent on the conditions you assume. So assuming these are the right numbers, these are the right probabilities. This is only 0.0002 higher. Okay, that's the real effect of not even, it's 1.763. This is only this much higher. That's the real size of the effect of this thing causing disease. It's very, very small. And so that's not even important necessarily per se, because this is, again, only of the people that we have measured so far. What if we wanted to look at this in in new people. And we'd have real models and all that kind of stuff, taking into account all kinds of other uncertain. We haven't done any of that, but just as a quick. So what we really want to apply this to new people is this. We want the probability someone's exposed, dosed, and gets the disease. And 1 million new people, say. Because we want to apply, if we're going to, what's the point of doing any of this unless we're going to make decisions based on, the future or something. So this right here is, what did I do wrong here? I got 3 zeros and an 8. I don't think I have anything wrong. Everything looks okay. Okay. Okay, so this is the probability. We just apply our total probability rules. Okay, this times the probability of D given EX times the probability of E given X. And from our numbers, we know that this is 0.008. We want to multiply this times this particular number here, which I just made up, 0.1. And that this right here, we got from our before, is 0.32. And this equals 0.000026. So this is this. And if I just write, let me write it all up here. The probability of Y exposed X, and that equals 0.00002, something like this. I mean this to be 10 times higher. Okay, so this is the probability in the next, whatever population we have, the people who are both exposed, dosed, and have the disease. This is the probability of the people who are both exposed and have the disease. This is going to give us the idea of the true risk in the population at large. And so in the next 1 million people, I hope you can see this, in the next 1 million people, there'll be about 26 people who have the dose and were exposed and have the disease. But people who are just merely exposed, it works out to be 202. I don't know if you can, I hope you can see that. In other words, in the next 1 million people, the people who are just exposed and have the disease, there'll be about 202 people in the next 1 million. In the next 1 million, waving our hands about the uncertainty in our little model here and all that kind of a thing. But of the people who are also dosed and exposed, there'll be about 26. So there'll be a lot of people that the real size is the difference here between this 202 and the 206. This is the real practical effect. Okay, this is 26, and this is still, don't forget, this is still not causative. It's indicative, it's evidence toward the substance, whatever this is, being causally related. But we know absolutely for a fact that there's other causes out there besides just being exposed to this. We've already proven that. We've deduced that from things. So they may be responsible for all this. So they may be lifestyle, I hate that word. There might be things in people's lives, other substances, other things, other genetics, all kinds of other things that lead them down this path of disease. And some of it may very well be the pesticide itself in this particular case. We don't know. But this has to all be bound. This is a sort of a grand risk calculation, not for the person, but for society. If you're going to try to make a decision, if you're a regulatory body or something like this, and you want to make a decision about this pesticide, well, you're going to get about 26 people out of the next 1 million. How many people's lives will be saved using the pesticide? How much more food? What is the benefits of health to using the pesticide? There's two sides to this. There's risk on both sides. And I don't even begin to do those kind of calculations here. Nothing like this. You can't just condemn everything because you can come to a calculation like this. You have to have it balanced among other decisions that you're going to make. And maybe this is the exact right decision. I don't know. Maybe it's the exact wrong decision. It all depends on questions that have nothing to do with probability or statistics or anything like this, because probability and statistics can't tell you what's right or wrong to do. No science can tell you what's right or wrong to do. That comes outside. We're not, the idea that the probability is telling us what to do is scientism. We're not psidolaters here. Okay. And we still haven't got to the most, the egregious example is when people substitute models for all these things and then forget that they've substituted models for them all. And we're going to review all that next time, which we'll do. And right now you can get more. You got to read the written lectures too. There's more material in the written lecture if you want to do this. And the homework is the same, to try to find some of these epidemiological studies and keep those questions coming. Right now, more at right below wmbriggs.com or wmbriggs.substack.com, WMBRIGGS. It's a lot of material and a lot of hand waving goes on here. And of course, I'm cutting out a lot of stuff. We can't get to everything. But this is in the direction of the right answer, all right. Believe me, I've done a lot of real life studies on this and confirm all of this. Okay, that's it for now. Thanks very much for sticking with this. I'll see you next time.